Alright, hello everyone. It's October 10th. We have another difficult one. Let's hope today we can get a little bit better than yesterday. But before we do so, let me just shut them off. Okay. Alright. Oh! I done this before. I don't remember though. You're given a zero-indexed 2D. Remember though. You're given a zero-indexed 2D array. Flowers. So flowers I. Start end means the ith flower will be in full bloom from start to end, inclusive. You're also given a zero-indexed integer array people of size n, where people I is the time that the ith person will arrive to see the flowers. Return integer array answer of size n, where answer I is the number of flowers that are in full bloom when the ith person arrives. So it doesn't really matter about the people. All you want to do is given a range, right? So basically given a range, and you say at a certain point of time how many overlap there are. So in this case, in 2 is 1, 3 is 2, 7 is 2, 11 is 2. So we can use a line sweep. All right, I think the official name for that method is line sweep. Basically, you will sort everything. I'm thinking that do we need to sort? Yeah, I think we have to sort. We're going to sort everything based on the start, right? Sort all the intervals based on start. And then, no, in this case, it's already sorted. No, it's not sorted. It's 1, 6, right? And then 3, 7, and then 4, 13, and then 9, 12. And now we do line sweep. Maybe it's not called line sweep, but anyways, every time we hit the left, we add 1, right? So I have 1 is 1, 3 is 2. Right? Oh, we have to, oh, I see. Yeah, we have to sort based on everything. And then 4 is 3. And then 6 is 2. Oh, shoot, inclusive, right? Holy moly. Inclusive. So when we hit it, we don't do anything. Huh. So maybe we should add 1. Okay, we add 1. It basically means at this point it's removed. 1 has got removed. Right? So now we say this is 7. Okay, next one 8. Next one is 13. That doesn't make any sense. Oh shoot, 9. I forgot 9. So 9. My bad. Now 13 is 1. And 14 is 0. Okay? So that's that. So when we have this, we can, now we sort this, right? And then we have map to all this. Then you give me 2, okay? So whenever you give me something, I binary search. I mean, I don't even need to do binary search. I just go, and then every time I go bigger than this, I do this, right? Move forward. So 2. I need to find the first one that's bigger, right? So I start with 1, but mine is 2, right? So I don't know, right? I don't know. What I know is I find the smallest one that's bigger than me. So 3. 3 is bigger than me. So I look to the one in front. So it's going to be 1. So at the 0, right? We can actually do 0 will be 0. Yeah, we should have a 0. Point 0, right? Or I could have just done like a 0, 0, 1, 1, 3, 2, right? So 1 is 1, or 2, we have 1. 3 is 2. 7, we have a 7. 7 is 2. 11. 11 should be 2. Yeah. That shall work. So let's try Java. So we need to sort this thing first. We can do that. Not really sort this thing. We need to do it. And we can say, 0 or 1. Okay? So I'm going to do a new thing. Together. Let me say int. Start and put together. Combined. Comb. Okay. Shall be flowers dot length times 2. Right? This is 2. And then we say for int tuple of flowers. Ooh, that's not right. For int I 0 I smaller than flowers length plus. We need I. Comb I. Holy crap. I think it's 2 times I. Right? Because you do 0, 1, 2, 3, 4, 5, 6, 7. So it's 2 times I equal to, now 2 times I 0 equal to flowers I 0. Comb 2 times I 1 equal to start, I do 0. Okay. And then comb 2 yeah, what if we start and end as the same position? Which is fine. The same position is fine. Or if we start and end. So at this position I will add 1 and a minus 1, which is fine. Every time I get a new position, I should take a look at the previous one, right? I think it's fine. So times I plus 1. 0 equal to flowers I 1. 2 times I plus 1. 1 shall equal to 1. So this is start. This is end. Oh! I can just say 1 and minus 1. Right? And once we're done... Oh! Why you keep saying this? It's stupid. No. It's yeah, you have to sort. So we have to do this one by one from left to right. I can't just say I'm at this position, I'm gonna minus 1, right? Because we want to know at that position what is the count. So I need a new thing. For that, I think the easiest one to do is to use a list. okay, a list of int counts, new array list, okay, and then I need to comp arrays dot sort com compare int is gonna be a tuple tuple 0. That's what we sort. Okay, we sort comp, and we say for I need count. Well, counts dot add new int 0 0, push 0 inside. Okay, push 0 inside, and then we say for int tuple of combination. Okay, then what do we do? Ooh, this I need a +1. Right, so what do? We need to first find out the current position, right? So int position and int count. Okay, so position is top 0, okay, and count shall equal to counts, okay, counts dot get counts dot length size -1 1. That is the count. That's the count. This count plus top 1. Okay, and then this is where we are going to make a thing, which is say if position is equal to the new position, if it's equal to counts.get counts.size -1 0. If the current position is the same as the previous position, then we simply say counts.get counts. Oh, it repeated 3 times. And last. Okay, so last equal to counts.size -1. So I don't have to keep doing this. Just last. Okay, last 1 shall equal to count, right? Else, if not, the current position is different, okay, from the previous position. If it's not, then we say counts.add new int position and count. Okay, now keep going until the end. I finish the whole thing. Now we're gonna do int. We will go. So I think I'll go through people, right? People will go for each one. I check on the counts. If counts is smaller, I keep going until it's bigger or equal to. We get out. Find its value. Okay. Find its value, push into the result, and then keep going. And then if it's still, yeah, so we shall do that. So we have a j. Okay, and then for int I equal to 0, I smaller than people dot length I plus plus. Okay. I just realized I don't really need to, but I should. And we need to get a res new int. This shall be people dot length. Right, and when this counts shall always dot add new int It's gonna be integer dot max value integer dot max value. It's kind of the last one. All right. So j is this, and we say while j is smaller than counts.length size and counts.get j 0 is smaller than people I. When that happens, okay, which means the current index, the time on the counts is smaller than the counts for this, so we have to keep going, which we'll do is j++. Okay, it's basically just j++ until we can do this, so we get out. When we get out, res I shall equal to counts.get j minus 1. Okay, counts.get j minus 1. 1, that's the count. And then we go through everything, then we'll return res. All right, let's give this a shot. It was not right. Fine. We'll figure it out. So we have flowers. It's gonna be int. Lordy, I have to do this. Oh, I can take just the inside. All right. Done. And int people. Oh, Popo. Ha. It's a typo. New int 23711. All right. Full bloom. Flowers, people. What was the problem? Dot to string. Call dot to string on array. Wait, is this not supposed to happen? Array dot to string. Okay. All right. So now what we need to do is let's put. Let me put it here. Okay. Let me just see. So let's see what counts. Okay, what counts look like. 0, 1, 0, 1, 3, 4. We can actually compare this to our drawings. Okay. So 0 is fine. 1, 1, 3, 2, 4, 3, 7, 2, 8, 1, 9, 2, 13, 11, 14, 0. Which is perfect. Right? It's perfect. So why do we get it wrong? Why do we get it wrong? So now we go through people. Okay, people. And we say, the counts, right? Counts is j. Counts is j. So we say if it's smaller, 0, smaller than people. People first is 2. Okay, so j++, smaller, j++. Right? And then Now we get out. Rest I equal to 1. Perfect. So j is here. Right? Now we'll go up. And it came out is 3. Oh, I think it should be smaller or equal to. Yeah. I think it's smaller or equal to 1, 2, 2, 2. Yep. I think the problem is that the only thing we change? Yeah, I think that's the only thing we change. Okay, now we have a problem on the second one. Jesus. Come on, man. How we have the problem in the second one? Well, we don't know, but we can speculate. It's okay. It's okay. We'll figure it out. 1, 10, 3, 3. Okay. This is 3, 3, 2. 3, 3, 2. And let's take a look. Counts. 0, 0, 1 is 1. 3 is 2. 4 is 1. 11 is 0. That's perfect. Right? Now we go for 3. We get a 2. Oh. Oh. Oh, you gotta be kidding me. You gotta be kidding me. I need to sort people too. Holy. Ugh. Okay. Yeah, we have to. Oh. I absolutely don't like this. But there's no other way around. So I need to sort people, but I also need to know. Oh my goodness. That's fine. That's fine. Okay. Int. People. Sorted people. Okay. Sorted people shall equal to new. Int this. People.length. This is 2. Okay. Then we say for int I equal to 0, I smaller than people.length, I plus plus. Sorted people I. Sorted people I 0 equal to people I. Sorted people I1 equal to I. Okay, so we do that. Then we do arrays dot sort sorted people comparator dot compare int top going for top 0. Okay, and no, we do this one later. Actually, we should do both later. Let's remove that. Yeah, we do both later. Get sorted people and attach their index info. Okay, so we do that and find the answer. Right, so we have this. That's fine. Then this is not people. Okay, it's not people. It is going to be sorted people. Okay, I is going with sorted people. Yeah, we probably should just go sorted people instead of calling it people. Okay, just making sure that we're doing sorted people, right? And then it's just smaller sorted people 0. If it's smaller equal to, we go. And then this is, that's not I. This is sorted people I1. Right? So if we do that, okay. 221. For loop can be replaced with the enhanced for. Oh, wow. Wow. This is just amazing. All right, yeah, you can do enhanced. That is true. It's enhanced. Help me, I mean, if you think about it, if I can put these in one line. No, I don't want to put these in one line. Good, no, I wouldn't say editor, no. Good ID. Okay, try this. Yes. Got it. Not too shabby, huh? Not too shabby. I'm calling it a line sweep, but I'm pretty sure it's not named this way. Well, anyway, that's 2251. The problem is essentially, all right, given an array of intervals, find the number of overlaps at any given time. It can be solved by counting at each interval start and end the current number of overlaps. Then we can go through, right? We can go through the desired time from left to right and find the gap. Find which gap it belongs to, and obtain the count accordingly. Now, I have been through this problem, this type of calendar scheduling problem 2 times with Google specifically. The first time was actually no, it was not. Yeah, it was good. The first time was, I think, back in 2019 for a summer internship. Problem was given as a HackerRank-ish online assessment. The second time was last year, right? I think it was last year, last October, when I was trying to October in a video interview, right, where almost exactly the same scheduling problem was asked. Both times, both problems could be solved by this method with some twists, of course. O1 log n. Actually, this is O1 log n. This is OON. This is O1 log n plus OM log n. And it doesn't really matter which one is M, which one is, right? Okay. That was good, right? One shot on this. Yeah, it was I was tested twice for Google, but unfortunately neither time did I get into Google. I mean, the internship I didn't get it, and The second time it's for a job and I didn't get it. Always getting stuck. All right, always getting stuck at the same process, the team matching process. So they have this difference array, binary search. That's the same. Simpler binary search. I don't even use binary search. Wow, I didn't even use binary search. This one's not binary search. Like, let's want to read through this. Actually, I don't want to read through. I want to see how I did in the past. You're kidding me. You're kidding me. My God. Is this the binary search method, huh? Okay, so I get, oh my God. So the starting position, 3 lines. 3 lines for a hard problem. My goodness. Anyway, let's figure this out. I mean, I wrote this myself. So hold on. So we're talking about binary search, and I have start end, right? And what do we want? So I put all the starting position where we start. It does make sense if you think about it. It does make sense, right? So if we pull all the starting point out, so we start with 1, 3, 4, 9. And each time we hit this is a +1, right? This is +1, +1, +1. And then we have all the end point. Oh, that's the same. That is the same. We have 7, 8, 14, and 13. And every time we hit this is going to be -1, -1. Actually, in this case, we probably shouldn't do that, right? We should use the original. We shall use the original because it's after we do -1. So it should be 6, 7, 12, and 13. So it will be -1, -1, -1. And then for given 2, binary search, right? It's in between. I mean, it will point into this, so it'll be +1. -2, that will be 0. Right? If you're pointing here, it's 0. What if you match to it? So we have to check if you match, right? If you match, you have to, what if you match? Match, you have to +1, right? Match, you have to +1. If you don't match, it's fine. Then this 2 does not match. I pointed to 0, so -0, so that's 1. Okay, 3 will be here. That's 2, right? That'll be 2. 7 will be here, so it'll be 3 -7. 7. We match to this. Oh, if you do 7, yeah, it's just 1. Should be -1 because you don't go up. You go over your -2, but 7 only -1. Wow, this is amazing. Holy crap. All right, this is a good solution. Yeah, this is my current method. The diffs, default dict. Default dict, you sort the time points. You do accumulate. Okay, num flowers. And then for each p, you'll bisect. Yeah. This one's fine. And I mean, it's verbose, right? Java is just verbose. Okay, I want to try the other methods. I think the binary search, the diff, binary search with diff is very interesting. So this is the binary search with diff method. It is essentially the same as before, but it might have simpler, but no, it has a much simpler implementation. All right, so we just get the start and get the end. I just remove everything. We don't need this. So we say int lows equal to new int flowers dot length. Okay, int highs equal to new int flowers dot length. Okay, then for int no yes tup no tuple of flowers lows I can't do that. I0 I smaller than flowers dot length I plus plus. This shall equal to flowers I0 highs I equal to flowers I1. Okay, so we got these, and then we say arrays dot sort loss arrays dot sort highs. Right, now we sort them. Yeah, sort all the starts and all the ends. Then binary search each position in people in starts and ends. The index of starts represent the number of flowers added, right? The index of ends represents the number of flowers removed. Right? Their difference is the answer. Boom. Right? It's a boom thing. All right, so int res equal to int this res equal to new int people dot length. Okay, for int I equal to 0 I smaller than people dot length I plus plus. All right, but let me also define two things. Low index, high index. Okay, now we say low index equal to arrays dot binary search lows, and what we're gonna put in here, we're gonna put people I. What if it matches? If it matches, it shall plus 1, right? So we shall say shall say low index shall equal to low index if it's smaller than 0, then it's low index plus 1, right? Because it's a minus this minus 1. Hold on, I forgot. That's BL3. Well, it's minus and by plus 1 negative. Yes, plus 1 negative, plus 1 negative. So plus 1, then we do the negative. This is fine, right? Otherwise, if it's not, that means we have found. If we've found it, then we shall say low index plus 1. Because if you find it's a matching, you need to add 1, right? So that's that. So high index, right, equal to arrays dot binary search highs and people I, right? Once we do that, high index equal to high index more than 0, and we do high index plus 1. Otherwise, we don't change. Once we're done, res I shall equal to low index minus high index. Then we can return res. Of course, this is O n log n for the sort, and plus m log n, because that's log n. All right, let's make sure this one's correct first. Yep, looks solid. Solid? Dude. We have an issue. Ugh. Expected 3. I got a little bit issue here. That's interesting. Not sure. Probably it'll be better if we take a look. Oh gosh. Ugh. Okay. Put them here. And okay, that's that. Oh, people is easy. There's only 14 and 4. So I think what we need to do is the same. I need to put it on here. Let's go debug, take a look. Oh, look at that. But it should be fine, right? It should be fine. Oh, 14. I see. Gosh. All right, I need to write a binary search myself. Bisect right. Int array int target. Okay. Int low equal to 0. Int high equal to array dot length. While low smaller than high. Int mid equal to low plus high divided by 2. If array mid is we want binary search on the right, okay? So if it's equal, we go. So if it's larger than target, right? The middle is too big, then high equal to mid. Else can say high equal to mid, else low equal to mid plus 1. So if it's equal, always low plus 1. So we do blah 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 blah. Once we get out, we'll return low. So now we have bisect right. Now these shall be much easier to deal with. I will redo this. In fact, I think I can directly call it. Shall you go to bisect right lows, right, people I, minus bisect right highs people I. Okay, let's run again. 3-0. There we go. Yeah, I have to roll our own bisect. You know what? I think this is what I'm gonna do. I'm gonna roll my own bisect left and bisect right, because I've done it. Right? I know how to write bisect left, bisect right. I know the bisect. Oh my goodness. I was just going to celebrate. What the hell? Oh shoot. Okay, I see. I know why. So bisect. Ugh. Can we handle this? The problem is with the highs, right? Because bisect right, you always point into the right hand side, which means you're not. So maybe hold on, maybe we can do it. So we'll do this +1. There we go. There we go. That's the one. That is the one. We have to roll our own bisect right. And for the ends, it should be one more, right, than the original to satisfy, to make bisect, to allow bisect right to work. Otherwise, we need bisect left, right? If we do not add 1 to the original end, we need bisect left. But I don't want to do bisect left, so we just do bisect right, which is perfectly fine. Yeah, it's Java, so you understand. The easier it gets, implementation wise, it also gets faster. Lightning fast, 35 milliseconds. Look at Python. Okay, so I'll just call it. I'll call it. And we have some time left. Let's just try to see what this one does. Let me turn off all of this. Yeah, I never really read this. I should save this. Save it into the downloads. A memoir of Robert Blinko and Orphan Boy. Alright, given a function and a time in milliseconds, return a throttled version of that function. A throttled function is first called without delay, and then for a time interval t milliseconds can't be executed, but should store the latest function arguments provided to call fn with them after the end of the delay. For instance, t equals 50 milliseconds and the function was called as 30, 40, 60. The first function call would block calling functions for the following t milliseconds. The second function call would save arguments and a third call argument should override currently stored arguments from the second call, because the second and the third calls are called before 80 milliseconds. Once the delay has passed, the throttled function should be called with the latest arguments provided during the delay period, and it should also create another delay period of 80 milliseconds plus t. Shows the throttle events. Each rectangle represents 100 milliseconds, and the throttle time is 400 milliseconds. So input event. Okay, so we'll throttle for 4, and then This is called, right? And then I don't understand. What the hell? Without delay, and then for a time interval t, it can be executed, but should store. So the latest function argument. So the latest one is called. So we call. First one called, but then this one, we just change the arguments, but it's throttled, so you cannot call. And you call this, you cannot call, but we overwrite the previous one. So now this is the argument, right? And then after 400 milliseconds, this one gets called. But should store the latest function arguments provided to call function with them after the end of the delay. So do we call it? We do. We just delay the call until that time. And then once we hit it, we'll call it. And then we'll hit a delay again. So t is 100 calls. The first call is always without delay. So calls to this. First call without delay. Second call will be 100. And with inputs is 2. We override, we do a call back. At 120 milliseconds. Why? Why 120? Oh, because we did first call at 50, right? And then we'll delay 70, so it won't be called until 120. So at a 120, we will call the latest arguments, which is 8, right? And that callback will make another delay, so it'll be 190. So this one gets saved in the delay, so it should be called as a callback at 190. Another one 260 is after, so it should be called immediately. Okay, I think I understand what this one is. How do we implement it? Right, we have a function, we return a throttled function. Throttled equals this. We call and logged at t, my t equals 100. Right. So of course you need to know if the function is still being delayed. One thing we can do for this, I think, we don't have to, we can keep a timer inside. Can we? Can we keep a timer inside? No, I don't think so. I think it has to be like set timeout, some sort of set timeout, right? So t, and then function need to call. So I will call it. Okay, I will call the function, and then I'll set a timeout. And during this timeout, during this timeout, I need to know if it is timed out, like, right? Because this function can be called again, so I need to check if it's timeout. I need to update the arguments, right? So something like, let's just play around. Let me just play around. So what I think, right? So we definitely need is throttled, right? So I probably can have is throttled. We default to false, and we can say latest arguments. We don't assign anything. That's fine. And then for this a function, so we can say if is throttled, then latest arguments shall equal to args. Done. Else, if it's not throttled, then we'll call function arguments. Right? We'll call the arguments if it's not. No, not this arguments, but the latest arguments. But what about the beginning? Because the beginning is false, but there's no. Oof. What about the first call? First call. I think we should always do this no matter what. Every time you call, we always do this. Then I just say if it's not throttled. Okay? If it's not throttled, then I make the call. Right? If it's not throttled, I make the call. Once I finish the call, okay? Once I finish the call, then what do? I need to do a set timeout. Okay? Set timeout, we have something. I don't know yet, but we're gonna set timeout for t. Alright? When t is hit. When t is hit, we need to set. So what do we do on this one? We can, maybe call this function again. Well, we can call this function again, right? Hold on, set timeout. When the time is out. No, I think when time is out, I should just change is throttled. What do you think? Yeah, what if I just, when time is out, I change this one to true? No, change it to false. But then when do we set it to true? After we call this, I set it to true. Right? So when you enter this function, so I have these two, right? When you enter, we return this function, okay? And then we call it the first time. We grab the latest arguments that's not throttled. We call the function. We set it to be throttled. Then we get into the timeout, okay? So in the timeout, and then you call it again, right? And the throttle remain true. So we just record the latest arguments. We don't go through this until this one set it to false again, and you call it again. All right, whenever you call it again with your current arguments. Now hold a second. You call at this, right? You call it at this, and then it's throttled. I save this, right? I save the current arguments, and then when the timeout is done, right? When the timeout is done, I shall call the function. I shall call the function with the latest. So this is not true. It's like I need a callback, right? I need a callback. which means this callback has to be, and when this callback called, I need to reset this whole thing, so I do have to call this function again. So something like this, we can say, you know, const inner equal to function, okay? And then we will return inner. And this, I'd like to make it look better. So I'll set this and I'll call inner with latest arguments. What do you think about this? So I'll set timeout, right, for t, and after t, we will go into, we'll set its throttle to false. So at this point, right, we'll set its throttle to false. And now I call this inner again, right, recursion. And when we call this inner, we have the latest arguments, which is saved previously. I reassign it, that's fine. And its throttle is false. I'll do this, right? I'll do this, and I'll set its throttle to true, and I'll set a timeout again, right? Set a timeout again. Now, but the problem with this is, after that, I will repeatedly call, repeatedly call. See, that is the issue. I need to know when there's no arguments. Yeah, like, how about this? Is throttled, okay? Then we say if, okay, if there, this is, yeah, it's false, right? It's not throttled. So if it is throttled, so it'll be like this. Else, if it is throttled, then latest arguments will equal to arguments, okay? If it is not throttled, right, then depends. If not latest arguments, then we will call this, okay? Else we'll call args. Then we'll throttle it again, right? Then we'll throttle it again, and I'll set a timeout. Now here, this is important, right? This is important because we're dealing with this situation, right? So we have something, so we call it, and after we call it, we need to set, how about this? After we call it, we need to set equal to null. We set it to null. Okay. We set it to null. And then here we say if latest is not equal to null, then I call. Otherwise, I stop calling. What do you think about this? Well, I'd say if initially we set it to null, okay, and then we do this is not equal to null, And I like to say if it's throttled, okay, then we say latest equal to arguments. Perfect. We understand that. If it's throttled, we don't make the function call. We just update the latest arguments. If it's not throttled, and not throttled happens, and initially it's not throttled, so we go in here. And latest argument is null, so we don't go this, we go here. We function, we call it, and then we set throttle to true, then we'll set a timeout. Only at the end of the timeout, throttle will be false. Okay, so now we're inside the timeout. Okay, inside timeout, we make another call, and it's throttled. We update the latest argument, right? Then we make another call, throttled, latest argument. So that's green now, okay? And then at the end, boom, it jumps out, timeout, okay? Timeout, we set its throttle to false. Now throttle to false, and latest argument is not null, right? It's not null at the moment. Then I call the inner again. So we call the inner with the latest arguments. So now we call this again. Now the is throttled is false, okay? Is throttled is false. So we go inside here. Once we go inside here, latest argument is not null. I'll make the call, which is corresponding to this, and I'll set latest argument to null. We don't have latest argument anymore. And then we'll set a throttle to true again, then we do this one more time, right? We do this one more time. Okay, now we're in the waiting. Now during the wait, this one calls again, so latest arguments, we get a value again, right? So now what I want to do is check this time. Okay, this time comes in, we do this, we basically update, right? And then we go through the same thing, latest argument equal to null, and then we'll call again. Now when we call again, because latest argument is null, once this times out, it will check if it's null. And because we haven't called again, so it is null, then we don't call inner again, then boom, we don't do anything else. This looks promising to me, so I'm gonna give it a shot. Doesn't work. Let's just check the first one. I think the first one does not work. What the hell? The first one works. Second one works. Third one works. Put them together doesn't work. I think I am polluting some stuff. I don't know, because if I put them all together, it tell me it doesn't work. Oh, now it works. JavaScript. Hola. Okay. Not too bad. But it's kind of late, so I don't have any intention to go through the solution right now. I'll probably do it tomorrow, right before we start. Feels a little bit hacky, right? Feels a bit hacky. I am pretty sure. I think, I'm not sure. I think the official solution will look different. Will be more elegant. Yeah, this is, if there's anything, it's not elegant at all. It just works. It just works. You know what? Oh. Yeah, you're not gonna use it. I think Lodash or whatever, it probably has this throttled version already. We'll deal with this tomorrow. But just based on a quick glimpse, right? You have two things, and I have two things, so it might be similar, right? And I have this. They have call the function set it to null. You see that? You see that? And do this. Yeah, it might not be that bad. It might not be that bad. All right. Anyway, I'll end today.